members of the state government. My name is Martin, and I am the project manager overseeing the design of the Table Tennis Championship Centre that you have proposed to us to design for. Firstly, on behalf of my team, MBSML Engineering, I would like to thank you for the privilege of designing this facility for you. As you can see, this is our final rendering design that we have made. From this design, we have taken into account several iterations and several different concepts that have been required in order to make the most economic but also the safest possible design parameters. We have had to consider several design elements when coming up with our final proposal, which are outlined extensively in our report. The first of the major elements that we have had to consider are the rafter designs. MBSML Engineering had to do several iterations in order to come up with the most beneficial members to use. Firstly, MBSML Engineering found that the best members to use for the rafters would be 610 UB 125 sections. However, we found that this would be significantly uneconomical, and as a result, we decided to look at our options in order to make this a more streamlined design. MBSML Engineering found that by adding 2 flag racing members to that purlin and that purlin would be sufficient in overcoming the immense loads that are imposed upon the sections. As a result, this provided a significant reduction in our member size, allowing us to almost halve the rafter size from a 610 UB to a 310 UB32. This provided a significantly more economical design and also was found to be a safer and much more secure member iteration. In doing so, we have used space gas programming as well as hand calculations, which are found in our report and verify that these are the most economical members to use.
My name is Ben, and I'm one of the engineers who helped develop the portal frame structure of the table tennis facility. After the rafter considerations, columns had to be analysed and designed. The initial parameter that had to be considered was whether a universal beam or a universal column should be chosen. And after several iterations, MBSML Engineering found that a universal beam would be the best option, as the universal column was found to be insufficient in taking the same bending forces as the beam, which in turn led to a more expensive member which had to be used. Subsequently, a design and analysis procedures found that a 310 UB32 is the most economical but safest member that could be used to support the structure.
My name is Sam, and I will be presenting the purlin and girt design considerations that had to be made for the facility. It was already predetermined that 0.48mm custom orb shitting with Z15019 purlins would be required when considering the design. However, our team had to analyse the various load combinations in order to ensure that the structural integrity of the facility was appropriate. According to guidelines, 1.2 metre purlin spacing are the maximum allowable distance for the roof structure. Subsequently, our initial calculations were in accordance with this requirement. However, upon investigating the purlin designs, MBSML Engineering found that a 1.2 metre purlin spacing sufficed within the given load conditions. This was the most economical design that could be created, as less purlins were needed overall.
My name is Latu, and I will be discussing MBSML Engineering's design considerations for racing and stability. Firstly, upon performing a stability check, we found that the facility had deflected too much from the calculated wind loads. As a result, cross bracing had to be added to ensure stability, which is presented in the diagram you see right here. Equal angle members were chosen for the tensile forces, while circular hollow sections were used for the compressive forces. Next, our team had to identify how to efficiently iterate the sections to obtain the most economical but safe members. In doing so, we decided that stronger bracings with lesser circular hollow section capacities would be more economical, as there were only 4 bracing members, but 10 circular hollow sections. In doing so, iterations found that the most efficient combination that ensured structural stability were the 48.3 by 3.2 circular hollow section members with 30 by 5 equal angle bracings.
connections details that were considered during the design. Now there were many connections that did need to be designed, but the base ones were the beam to beam connections, beam to column, and the bracing connections. Now MBSML Engineering did determine these connections through both bending and shear conditions. Now with the member-to-member designs, we did use a bolt plate joint to connect them. However, the column connections did require plate stiffness to appropriately carry the imposed loads, and in doing so, design the most effective and economical design without having to increase the size of the members. Now, these larger members would impact the economical value by a considerable amount, which is why we did go with the other option. With this, we do believe that the members are both safe and efficient in terms of cost and stand safety, which is an element that our team does pride ourselves on quite highly. Now, for the final element, which was the cross-bracing connections, as you can see here, we did use a full penetration butt weld as our connecting element, which again increases the safety factors considerably whilst also being rather cost effective. Overall, you can see that MBSML Engineering has taken several design factors into account to optimise the proposed design in a manner that was both economical and safe. Our design has been created in accordance with the Australian standards, subsequently emphasising the importance of safety that MBSML prides itself upon. However, we have also attempted to iterate the most economical design on behalf of yourself, the state government, and as a result we would like to again thank you very much for considering us in your design process, and we hope that you approve of our final design. Thank you.